Hello, and welcome to AMAT362, Probability for Statistics at UAlbany. This is Lecture 9. Today we're going to discuss the three M's, mean, median, and mode. One of the key things I want to make sure that everybody understands coming out of this lecture is that these are all different. They're all different. I want to start to do this by first going through some of the geometric distributions or random variables that we've already encountered in last lecture, before we get to this more general discussion of mean, median, and mode. So let's recall from lecture 8. The first thing I want to recall is the binomial random variable. This was the random variable which counted the number of successes out of n attempts at something. So suppose you flip a coin 10 times, I'm going to count the number of heads that occur out of those 10 flips. So this is the this is the random variable that counts the number of successes out of n tries. So we sometimes write this random variable using different letters. I like to use Sn to indicate that this is something that counts success S out of n tries. All right, so this is going to be my binomial. So remember that the way that a random variable works is it assigns to outcomes. So these are sort of elements inside of our sample space, omega, numbers. Now, this seems like maybe a silly distinction, but if you think about it, when I'm flipping a coin, I'm counting heads or tails. Those are the actual outcomes. But there are various ways of representing heads and tails numerically. I could just say a heads is a 1 and a tails is 0. That's what gives rise to what's called the Bernoulli random variable. But by summing up these Bernoulli random variables, we get the binomial random variable. We'll see that in more detail in future lectures. But just as a quick recap, we would say that the probability that of k successes out of n tries is equal to n choose k times p to the k times q to the n minus k, where p was our probability of success on any given try. Alternatively, we could write this as the probability that Sn equals k. Again, Sn being the letter that we're choosing to represent the binomial random variable. Or we could have called this probability sub Sn of k. And then sometimes it's convenient to drop the subscript of Sn if we know that we're talking about the random variable Sn, which counts the number of successes, and just focus on what's the probability of k. It means number of k successes. Now, it's convenient to represent these values in a Pmf chart, probability mass function chart. So let's go ahead and spell that out here. So if I do this, it looks something like this. You might want to call this the Pmf notation. This stands for probability mass function. And what you can do is just write it out like so. You start by listing the possible values for k. And we can write this as the probability of k. And of course, if I try n times, I can succeed 0 times. What's the probability of that? Well, that's equal to the probability of failing n times. That's given by q. Q is 1 minus p. Q equals 1 minus p. Additionally, I can then ask, well, what's the probability of succeeding 1 time? Now, this is 1 time out of n tries. So you might think it's just p times q to the n minus 1. But that's actually not right, because you could have succeeded on the first try and then failed a bunch of times. Or you could have failed the first time and succeeded on the second try and failed the remaining times. And if you consider the possible ways of succeeding 1 time, it turns out to be n. So that's equivalently n choose 1. And if we keep going, write down the general formula, we get exactly the thing that I just wrote above. So it's n choose k, p to the k, q to the n minus k. But if I keep going, the largest possible value of a binomial random variable is n. And then this sort of looks symmetric, where I have to see the probability as I had to succeed every time. And there's only one way of doing that. And so, thus it suffices just to take p to the n. Now, one of the things which you might observe is that when p equals q equals 1/2, these probabilities actually look to be somewhat equally distributed around the middle value for k, so where k is approximately n divided by 2. And so I might represent this using a little spike chart like this. And so this corresponds to roughly n over 2. Of course, if n's not even, then n over 2 is not going to be an integer, and so it's not even a possible outcome. We're going to see today what the sort of significance of this sort of symmetric distribution looks like, at least in the case where p and q are roughly 1/2. And this is going to get to this concept of there being sort of an average value that's concentrated around the middle. So this is a graph of roughly the probabilities. So here I'm drawing probability of k on this axis, and over here my other axis is k. All right, so let's also recall our other canonical distribution. And this is the geometric random variable. And this is the thing that counts the number of tries required to reach your first success. So this is the random variable that counts number of tries needed for first success. And so this is a little bit easier. Formula for this, sometimes we use the variable maybe tn, or I should just say t. That's our random variable for this. And so here the probability that our first success is on the kth try equals, we had to fail k minus 1 times, and then on that last try you finally succeed, which happened with probability p. So alternative notation for this is sometimes probability that t equals k. And if we did the same sort of thing where I look at the distribution of possibilities, then, you know, it turns out that the most likely outcome is that you succeed on your very first try. So this corresponds to k equals 1. Because each of these q's are numbers less than 1. And so when you keep multiplying, that's going to keep shaving off the probability. If I try to connect the dots, it's going to kind of have this almost exponential distribution where it's sort of tailing off like this. It has a horizontal asymptote at a probability equals 0. So it's the same sort of thing here where I'm graphing the probability of t equaling k. And this is k equals 2, k equals 3, so on and so forth. Now, it's really nice to look at these pictures here. So just to go back, here I'm looking at two very particular situations. I'm essentially repeating a single task which has one or two possible outcomes, success or failure. And in the binomial case, I'm looking at n tries and I'm counting the number of successes. And it turns out that there's this general formula which uses these sort of choose coefficients. And in the case where things are evenly balanced, this curve looks sort of nice. But in general, it could also look a little weird. It could look like this, or even, you know, be tilted the other way. All depending on what the values of P and Q are. And studying the limiting behaviors for P and Q in these different situations is going to be a subject for the next several lectures. Similarly with this geometric distribution, it's nice to see a look at this long tail of possibilities. And in particular, what makes geometric different than binomial is that, you know, k can be arbitrarily large. You could try literally a million or a billion times, and still not succeed. But, you know, in the limit, the probability of not succeeding for that far goes to 0, and thus the probability of succeeding at least once goes to 1. But we're going to be interested today in 3 different ways of summarizing distributions. And these are sometimes called summary statistics. So today, we're going to be studying 3 summary statistics. These are the ones that are the title of today's lecture, namely it's the mean, the median, and the mode. So I'm going to go ahead and give quick informal definitions of each of these 3. And the key idea with a summary statistic is that it should be sort of a one-number summary of your distribution. Instead of having to carry around all these formulas, you can just literally say one number. So this is the summary statistic is already a thing of interest. This is a number, a single number that summarizes a probability distribution. Which we think of a probability distribution as being this thing which summarizes how a random variable behaves. All right, let's continue. So what are our three topics today? So our 3 summary statistics. Well, these are the mean, you want to think of the mean as just another way of saying average. This is also the same as, so also known as the average or expectation. We think of the average as something that sort of happens empirically. So I collect data, and then I get a list of numbers, and I can add these numbers up together, divide by the total number of numbers, and that's average. But I could also think of this as like, if I'm modeling an experiment, which is fundamentally random, what do I expect to occur? That's the term expectation. All right, and so we're gonna sometimes use the symbols mu, which is the same thing as x bar. This comes from adding together a bunch of numbers and dividing by n. Or more formally, we're gonna write this as e of x. This is our expected value of x. And all of these are interchangeable: mean, average, expectation. So we think of this as the empirical. So this is, first of all, this is the Greek letter mu. Yeah, it looks like that. And this is the empirical average, which we sometimes call x bar. All right. The second summary statistic is known as the median. As you might imagine, it's supposed to be talking about the middle of a distribution. And it actually means exactly that. So this is our number where, so this is where 50% of outcomes of x being our sort of random variable, you could think of that as grades on a midterm, for example, where 50% of the outcomes is below the median and 50% above. So it's the middle point. But one of the things we're going to discover is that this is in general not unique. In particular, there might be lots of values where 50% of the outcomes are either below or 50% are above. The third summary statistic, and I trust that many of you have seen some version of all of these, but we're going to go through it today in a little more formal, rigorous detail. So the mode, which you should think of with mode, is most. It's the most likely or the most probable outcome. It's the most probable outcome or value for some random experiment or random variable x. And this is also not unique. And again, in both these cases, what I mean by not unique is that there are examples where it's not unique. So that means in general, it's not unique. But in some specific cases, it is unique. And so there is a single median and a single mode. All right, let's move on. All right, so key thing, so key fact. So nota bene, no well. All of these are different. Let me show you an example. This is a very, very concrete example. All right, so in this example, I'm going to imagine I have 4 people who have taken a test. So 4 people take a test. And I know this is a random experiment because I don't know what these people are going to get on their tests before they actually take the tests and produce a number. And I got 4 people and each of them might test differently. I mean, that's in general what we see. So let's say in this case, and maybe I'm like making this just an exam out of say 5 points or something like that. And so with that case, there's only a limited set of possibilities. Let's suppose that, you know, 2 people get 80%. And the other 2 people get perfect scores, 100%. Now, if I want to compute the mean, one thing I can do is I can think of taking the empirical average. So here I have the empirical. Empirical just means sort of what I see when I look at these outcomes. So empirical average we sometimes call this X bar. Well, the way I would compute X bar is I would just take, all right, somebody got an 80, another person got an 80, somebody got 100, another person got 100. And then I take those scores and I divide them by 4. If I do that, you'll see that I get 360 divided by 4, which if you think about it a little bit, it's 90%. All right, cool. And that kind of makes sense. So, you know, I'm gonna go ahead and let's imagine that again, here I have my, I think of this as my number of people with that score, and here I'm going to have my score. And so in this case, yeah, I've got 2 people who got an 80%, and I've got 2 people who got 100%. Or maybe sometimes like thinking of this in terms of a histogram, in which case, you know, maybe I draw little blocks around them that group everybody who are within a certain score range. And then I can just think of it like this. So you can see that the mean, the average, sat right here. That was our 90%. That was our average. So it looks like it sits in the middle here. But you might say, well, wait a second. I thought the median was the middle. I mean, and indeed, let's recall, all right, what is the definition of the median? So here's more formally, I would say any number m with the probability that x is greater than equal to m equals 1/2, which is the same thing as 50%, and probability that x is below m equals 1/2, and this is equal to 50%. Now you might start to get a little confused here because you're going to say, well, hold on. When I was looking at this histogram over here, I said I've got, all right, 2 people, each with scores in this range, but we just go ahead and call them 80 or 100 because maybe they're only 5 points on my exam, and 2 people got 4 out of 5 and 2 people got 5 out of 5. How do I think about this as a probability though? Well, you can always associate to a collection of numbers that are produced by some experiment like this, an empirical random variable, or probability mass function. So here we can look at the empirical Pmf, probability mass function, where what I do is I say that the probability that x equals k is equal to the number of times k appears in a list of n numbers, and I divide that by n. So this is just to say that, all right, I can rescale this, and I could divide this by 4, 2 divided by 4, and this would also be 2 divided by 4. And so in this case, I could say that the probability of someone getting an 80% is actually 50% because half the people got 80%. What's the probability that somebody got a 100 on this test? Well, it's 50% because 2 out of the 4 people got 50%. So if you think very carefully in our example here, here, any number m that's in the range between 80 and 100, but not including that endpoint of 100, is the median. So any number here since we have medians, right? Because if the second I get up to 80, I can say, oh, yeah, 50% of my class had an 80 or less. And 50% of my class had an 80 or more. But I could also say that with 85 or 90. Only number I can't say that for that's above 80 is 100, because 100% of the people in my class had 100 or less, because 100 was the maximum score on the test. So here's a situation again where the median's not unique. But you might go ahead and just pick one in the middle and say that's the median. I'd say the general rule of thumb is people take the smallest number, which satisfies this property of 50% being above, 50% being below. All right, but we've got one more summary to consider, and this is the mode. So what's the mode? Well, in this case, both 80 and 100 are modes. So this is the most probable. i.e., you might think of it as k such that the probability of x equals k is the maximum possible value. But in this example, they're both equally likely. And so in particular, both 80 and 100 are the mode. In this example, both 80 and 100 are modes. And so you could think of this as a bimodal, meaning two-mode distribution. Let's consider another case where maybe these numbers are a bit better defined. So let's do some more examples. Maybe let's go ahead and harken back to our geometric distribution. So here I imagine I've got, I'm gonna do my little spike train here, where here this top value is P, and this corresponds to K equals 1. It's probability of succeeding on my very first try. Or I could succeed on my second try, which is going to be Q% of P. And that's going to be Q times P. Again, Q is less than 1, so it has to shrink P. Same thing applies for K equals 2 or K equals 3. So now I have to take again. Now Q times P, which I can just write as Q squared P. And if I just keep continuing this, you'll see I've got this long set of possible values, and you might just guess like what is the mean and the median and the mode for the geometric random variable. So what's the mean? Well, intuitively, let's say P is 1/10. So that means if my chance of success on any given try is 1/10, how many times do you maybe expect to need to try before having your first success? Because again, that counting when that first success occurs is the definition of geometric random variable. Well, you could say that the expectation of T should be 10. So it takes 10 tries on average to have your first success, which sort of goes way out here. That's our expectation of my geometric random variable T. But what about my median? Well, this is sort of a tough calculation. But in last lecture, we did this sort of gambler's rule where we said, how many times do I need to try to guarantee that my first success occurred before that try number 50% of the time? Roughly, it looks something like, if I had 1/10 was my success, then something like 69% of 10. In general, the answer is more like log base E of 2 times 1/P looked roughly like the median. And so notice that number's less than the mean. So in this sense, the median ends up being something that's more like around here. And what about the mode? Well, the mode was the most probable outcome. So just looking at this picture, what's the most probable outcome? Meaning, what has the highest probability as I scan through my possible values for K? Well, remember, these spikes here are supposed to indicate the probability. So higher means more probable, lower means less probable. So actually, this is very clearly our most probable outcome. So this has the kind of counterintuitive effect that in this geometric random variable, the most likely outcome is actually that you succeed on the very first try. I know it feels a little weird, but again, your eyes can't deceive you here, and math can't deceive you either. So most likely, is K equals 1. So then this ends up being our, just to switch colors up a little bit here, this ends up being our mode, is K equals 1. So all three of these things are different. In order to understand this for the binomial, we're going to need a little more machinery. So I'm going to put that off for another lecture. Let's go do some more basic examples, things like rolling die and what have you. And let me just go ahead and remark that when I looked at my last example, where I got 4 people taking a test, 2 people got 80s, 2 people got 100s. I kind of talked through this and turned it from a histogram into a probability distribution, or specifically it looked like the probability mass function. And I called this the empirical Pmf. Let me go ahead and formalize that a little bit. And use that as a motivation for generalizing my definition of the mean or the average or the expectation. So example 1 revisited. So here I can turn grades, especially when they have repetition, into a random variable. And in this case, it looks something like this. So here I look at my possible value k, and then I have probability that x equals k. Well, there were only 2 possible values. I guess there are more, but those had probability 0, so I'm not going to write them down. And so the probability of getting an 80 was a half, and the probability of getting 100 is a half. So another way of computing this average, x bar, was to take 80 times 1/2 plus 100 times 1/2. Now notice this is different than what I did before. Just going back briefly, when I computed my empirical mean, IS right here, what I do is I took 80 plus 80 plus 100 plus 100 divided by 4. It gave me 360 divided by 4. But here, when I'm going to compute it, I'm just going to take 80 times a half plus 100 times a half. And what do I get? Well, that's obviously 40, and this is obviously 50, which equals 90. It's another way of computing the average, where I've built in, instead of just summing the number twice, I've now recorded that as the probability of that score occurring was a half. So here's the general theoretical definition of mean. So here's the general theoretical def of mean. And it's going to look something like this. So here's the definition. So if x is a discrete random variable, then the mean or expected or expectation of x is E of x, which is defined to be the sum over all possible values k, where I then take k and I multiply it times the probability that x equals k. So this is super important. What's nice about this is, as long as you have a formula for your probability mass function, those are the entries stored in this table right here, for example, then I can just take the value, the outcome, and I multiply it by the probability of that outcome. And then I sum up across all possible outcomes weighted by the probability of that outcome. And that gives me the expectation. This is also called the average. We call that E of x. So we already saw how that worked here, and we saw that it actually agreed with the empirical average, where we just add up all the numbers and divide by the total number of numbers. Let's do some more examples that leverage this this example right here. So here's another example. Oops. So imagine I roll a 6-sided die. And I'm going to let X equal the number that's face up when I roll the die. So it's the number that is facing up. Of course, there are 6 possible outcomes, just corresponding to the fact that if I write down my Pmf table, and here I have a probability that X equals K. We know that, assuming this is a fair, unweighted die, that each of the outcomes 1, 2, 3, 4, 5, and 6 are equally likely, and each of those has a probability of 1/6 of occurring. So this is also sometimes called the uniform distribution on 1, 2 through 6. And again, this is just the product of rolling my question of how many dots is on each side, so on and so forth. All right, so now let's compute expectation of X. That's the expected value of this dice roll. So E of X in this case is, well, if I want to be really formal and write it down, I need a sum over all possible values. So it's K equals 1 to 6. And I need to take that value K and I need to multiply it by the probability that X takes that value. Okay, so this looks really, algebraic and really sort of complex, but if you think about it, it's not so bad, because all this is really saying is, if I write it out long way, so this is 1 times the 6th plus 2 times the 6th plus 3 times the 6th plus 4 times the 6th plus 5 times the 6th. Oops. Plus 6 times the 6th. All right, might be tempted to go ahead and cancel that 6, but I wouldn't do that yet. So let me rearrange this a little bit and realize that a 6th is a common to all of this. And so I just need to figure out actually what's the sum of 1 plus 2 plus 3 plus 4 plus 5 plus 6. And if I can figure out that sum, divide by 6, then I'm golden. Well, you could sit down and do it, but this is actually a great learning opportunity. How do you sum the collection of numbers from, let's say, 1 to n without having to actually add them all up bit by bit? So this is something called triangular numbers. So I'm going to do a quick aside on triangular numbers. And the reason why we call this the triangular numbers is because in this setting, if I were to arrange that last number as the base of a triangle, I could build it all up like this. So what we're studying here in this particular calculation is 6 triangular. That's 5. All right, good. And you can kind of check that. All right, if I'd done a little bit better, or I could have cut it this way or this way. Either way, it organizes itself into a triangle, and the answer is it's the number of dots in this triangle. So Tn equals the number of dots in a triangle with n dots. It's on the base. And so there's actually a really nice way of doing this, and there's a good story around this. So famously, this mathematician Gauss, when he was a child, even back in like elementary school, teacher one day was really upset, didn't want to deal with the students anymore, and just said like, okay, everyone, you need to figure out. She said, Gauss, little Gauss, sum the following: 1 + 3 + 3 + 4, all the way up to 100. The teacher sat down thinking they could just, relax for the rest of the day, read their magazine, and not have to teach these students anymore. And little Gauss sat there for a bit, had a really clever insight, and then handed in the answer just a few seconds later. So the teacher was like, oh my gosh. And what Gauss realized was that, and again, you're only given these small little chalkboards they had to do on, they didn't have paper back then. So, well, if I took this list of numbers and I reversed it and wrote it right below the original list of numbers I was trying to add up, and I looked at adding each of the columns, so adding this and this and this and this and this, they all actually equal the same thing, which is, 101 plus 101 plus 101 plus 101, all the way down 100 times. So it turned out that if you sum these up, well, again, there's 100 of these, so there's 100 times. And that's just the same thing as multiplication, right? So adding something to itself, k times is the same as multiplying by k. So the value of this sum was 100 times 101. But Gauss added in this little extra copy of the original sum below it, so you only need half this value. So that ends up equaling this divided by 2. So you can just figure out it's 50 times 101, and then that's a lot easier to do. So how do we do this? So let me just go ahead and say, for the record, this is the same thing as T100. And so that in general, if I were to, take in and do Tn, I'm gonna go ahead and write it here. I'll do it in green. So Tn equals, well, it's the number you're trying to sum up to times n plus 1 divided by 2. And so in particular, if I look at the case where n equals 6, this is like our die case, then it's 6 times 7 over 2 is 21. And so there turn out to be indeed 21 dots in here. And in some sense, you can kind of see, why that works. If I were to take this, copy it, maybe paste it here, maybe shrink it down a little bit. And then let's imagine I copy that again. Copy, let me paste it. And now let me flip this around. Now you can just sort of see that there's 1, 2, 3, 4, 5, 6, 7 on each side. And then I've got times 1, 2, 3, 4, 5, 6 times 6. That's 42. The answer to life, the universe, and everything. But I only need half of that, so I just divide by 2, and that's how I get back to my 21. So what does this all say? Let's go back briefly. So I can finish my calculation very simply if I know about triangular numbers by saying that this is, well, oh, this is 1 over 6 times 7 divided by 2. I can factor out those, and that tells me that it's 3.5. That's the expected outcome. Now, isn't that strange, though? We'd say expected outcome, but it's actually an outcome we'll never see. So it's the average outcome, meaning that if you were to roll the die a bunch of times and then like write down the outcome and then take that list of numbers and add them all up and divide by the total number of times you rolled, you should get a number that's approximately equal to 3.5. So just, I'll leave it to you, or we can consider it in class to figure out, well, what can I do for an insided die? You play Dungeons and Dragons, you just roll a 20-sided die, D20. You can figure out what's the expected outcome or average outcome. But all this is now leading me to build up to the following story. This is the final bit for today. Is that although we have these 3 summary statistics, there are also 3 ways of thinking about average. And average, or E of X, is going to be the most important one for now. So let's do that. So there are 3 interpretations of E of X. So the first interpretation is that this is the long run average. In other words, if you perform an experiment enough times and record the outcome, I just call it the outcome X, then the empirical mean, so the average value, which equals same, also called empirical mean, should correspond to the expected value when computed using the formula for E of X. So these should be close. So I'm going to say this is very close to. And we're going to later actually see what that kind of, how close we actually mean by very close. And this is going to get to something later called the law of averages. So the second interpretation of mean, or expectation of E of X, is we want to think of this as the center of mass. Or some people call it the center of gravity of the probability mass function of X, where you imagine that these sort of spikes have weight. So this is probably best illustrated with an example. So here, imagine again, I have 4 people who take an exam. And let's say the scores are a little different this time. I still have my two people get hundreds, but I've got somebody who gets a 20, another person gets a 40, so not doing so well. But again, there's always time to improve. So let's say I've got my, right here's 0, 10%, 20%, 30%, 40%, 50%, 60%, 70%, 80%, 90%, and 100. And let's imagine instead of those little spikes, I've got these, blocks. That's a student. That's another student. And so I've got another block, another student sitting at 40, and I've got another student sitting at 20. Now just imagine that my real line or my axis of possibilities is like a plank of wood, and I've got these big sacks of sand indicating what percent of the class performed there. And then ask, where would I put my finger, on this, on this plank of wood to get it to balance. So if the fulcrum there, how would this distribution balance? Well, let's just go ahead and compute it. So if we computed my empirical mean, this is X bar, well, it's 20 plus 40 plus 100 plus 100 divided by 4. So that's 260 divided by 4, which is 65. So that says here that actually, here's my X bar. It's right there. So that's interesting. I mean, it kind of makes sense. It sort of drags a little bit to the right because I've got these two blocks here sitting at 100. What happens if I remove? So if I were to remove, let's say 40, then what would I get? I would get a new calculation for X bar. I'd get 220 divided by 4, which ends up equaling something like 73.3 repeating. So that actually looks like, here I could put my fulcrum here. So it shifts a little bit to the right, but not as drastically as if I, for example, removed 20. Then what do I get? I get 240 divided by 4, which is, sorry, I messed this up. So it should be 3. So I got 240 divided by 3. Now that actually equals 80. So then there I would have a fulcrum that's way out there. And so all this is to show you is that somehow distance from the center more strongly impacts. So in this sense, expectation sensitive to outliers. So the impact of each of these is different. So just by removing literally one student's score, in one case I changed the average only 8 points roughly. In the other case I changed the average by 15 points. This also should show you that in cases where, so for example, so I'll just say, well, that for uniform or, symmetric distributions, the mean is right around the middle. And so we have a situation here where, you know, for example, for dice, or six-sided die, I've got a 1, 2, 3, 4, 5, 6. And so we're going to put, you know, sort of piles of sand of equal weight. And again, I kind of stretch things out a little bit, but you can see that this is where our median is, our expectation of X. That's also where empirically we'll see numbers concentrate, or at least average out to, not actually concentrate. Or if I wanted to say, imagine I wanted to count, say, let's say flip a fair coin 4 times and count the number of heads. Well, I'd have something like this where I could get 0 heads. I could also get, I could get 1 head. I could get 2 heads. I could get 3 heads. I could get 4 heads. And if I think about what each of these piles of sand look like, or I think about the histogram of actually flipping a coin and counting and binning appropriately, you know, I'll get stuff that looks like this. And again, you'll see that the mean or expectation, in this case, centers around, well, 4 times 1/2, that was your chance of getting a heads, which equals 2. And we'll see why that is in general. Notice here, again, something worth observing, that all of these so I'm just going to say, notice that every outcome is equally likely. So the mode is any one of the numbers 1 through 6. But here there is a unique mode. And also this median calculation works out to be, you know, show that the median roughly agrees with the mean in these two situations. So, all right, and then for my very last example of how to think about expectation. So you want to think of this as the fair price or you want to think about this as the gambler's winnings. And so this is best illustrated via 2 examples. So suppose you rent a car and they offer you extra insurance for $200. Should you buy it? Well, you want to consider there are 2 scenarios here. So you can think of these scenarios as specifying different random variables, different outcomes depending on what happens. So if there's the no insurance, let's say that the amount extra that this car rental is going to cost you is witnessed via some variable X, then there are going to be two possibilities. One is, let's say maybe a $2,000 accident with probability P. And then, you know, of course, 0 if no accident occurs with probability Q, which is 1 minus P. The other one is where you buy the insurance, Y. And what that means is you pay, you know, $200 regardless. And so the only way to understand whether or not insurance is worth it is you need to compute the expectations of these two random variables. So it's the insurance is worth it if the expectation of Y is less than or equal to the expectation of X, because that's the expected amount you're gonna have to pay underneath these two different scenarios. So obviously, expectation of Y is just is $200, and you pay that with probability 1. But the expectation of X is, well, you know, there's two things that could happen. You might not get in an accident, so that's $0, and that's since you kind of gained $200. That happens with probability Q. Plus, then there's the $2,000 accident, which happens with probability P. And here I'm making the simplifying assumption that, all right, obviously there's a whole spectrum of things that can happen that cost a different amount of money, but let's say that the average cost of an accident is $2,000. All right, well, you could just see it here. So it's 2,000 P has to be greater than or equal to 200. So 200 has to be less than or equal to 2,000 P, which is the same thing as saying that P needs to be greater than 10%. So that means that if you personally have more than a 10% chance of getting in an accident, then you should buy the insurance. But if you're confident in your driving abilities, then and you don't think it's that high, meaning your chance of getting into an accident is like maybe 1%, then with expectation, you could actually save yourself the money and not do it. But of course, if you don't have the capital to cover such an accident, then that could be ruinous, and maybe you just want the peace of mind. The real reason why you shouldn't buy car insurance is that if you use a major credit card, it usually comes with extra insurance already built into just using a Visa or something like that. Anyhow, so the moral here is that if you are less than 10% likely to get into an accident, don't buy it. All right, and then of course there's similar situations where if I want to know if I'm buying a lottery ticket, is it worth it? Well, it's a question of comparing the expectation of the winnings versus the expected guaranteed payout. But anyhow, that's something we'll discuss in another lecture. So I thank you all for your attention, and I look forward to seeing you soon.